So we spent the last video looking at magnitude and direction. They're the two factors which define any vector that we know. What I'm going to do in this video, I'm going to set you a couple of questions based on these. I want you to read the questions, pause the video, have a crack, and then come back and check your answer with the worked solutions here. Here you go. So 3 questions. First one, calculate the magnitude of the two vectors below, so A, B, and C, D. Second one, if the magnitude of the vector xy is equal to 4, and xy takes the form x and 3, what are the possible values of x? And the last one, calculate the vectors below in terms of q, r, and s using the triangle scenario that's there. So the vectors qs, pr, and qp. Pause the video and have a crack. So the first question, calculating the magnitude of these two vectors. Remember, the magnitude of a vector is given by the sum of the squares of all the terms, then you take the square root. So we know then that the magnitude of the vector AB, because it's only a 2D vector, is given by the square root of x squared plus y squared. Now x is the x component, y is the y component, so we can simply say it's given by the square root of 7 squared plus negative 4 squared. 7 squared is 49, so it's the square root of 49 plus negative 4 squared, which is 16. 49 plus 16 gives you 65. So it's the square root of 65, which gives me 8.1 to 1 decimal place. So the size of that vector is given by 8.1 units. Second vector CD, well, this is a 3-dimensional vector, but it's still the same basic logic. So the magnitude of CD is still given by the sum of the square of each term and then the square root. It's just you've got 3 of them. So it's x squared plus y squared plus z squared. There's a third direction involved. So that gives me the square root of x squared, so 4 squared plus negative 3 squared plus 2 squared. So that's the square root. 4 squared is 16 plus negative 3 squared, which is 9, plus 2 squared, which is 4. Gives me the square root of 29. Square root of 29 is equal to 5.4 to 1 decimal place. It's 5.4 units. So there you go. Calculating the magnitude of a vector, fairly straightforward. We follow that logic. Sum of the squares of all the terms, take the square root. This one here, if the magnitude of xy is 4, and this is xy, find the possible values of x. This one's kind of flipping it on its head. We're given the magnitude, we have to work our way back. So what we know then, the magnitude of xy, we know is going to be given by the same formula, root of x squared plus y squared. But we know that that's going to equal 4. It's now a case of substituting in and solving the equation. So in this case, it would be the square root of x squared, our x term, plus 3 squared equals 4. So now we have that, we take the square root over, and we have a go. So we then get x squared plus 9 equals, well, to get rid of the square root, we square it, so that equals 16. X squared plus 9 equals 16. X squared equals 16 minus 9, which is 7. So x equals plus or minus root 7. Now, I put plus or minus here because it says possible values in this question. However, bear in mind that if the question states that, you have to use logic as well. You can't have a negative length. The length of something's always positive. So in this case, the length is given by plus root 7. So I know that the length of my vector is going to be given by root 7 units. So there you go. We have to use a bit of logic when we're doing this as well. Remember, we can't have a negative length. You can't say you got negative 100 miles away. Our final question is calculating the vectors below in terms of the vectors q, r, and s when we have this scenario here. So I want the vector q to s, p to r, and q to p. Now the vector q to s, what that's given by is the journey from the point q to the point s. So from up here all the way down to there. So it's a vector pointing this direction here. And goes all the way down. So what we have to do is figure out how we make that journey. Well, we go from q to r and then r to s first. Q to r, well, the vector's called r, but it's pointing the opposite direction. So we have to go back the way, so we have to go negative r to start. We then go from r to s. Again, the vector q goes from s to r, so we have to go back the way in this. It's then minus q. So there you go, our vector qs is equal to negative r minus q. The vector from P to R, well, that one is going from there. So the point P across to the point R on this side, we need to make that journey somehow. Well, to make that journey, we have to start at P, we go along to S, and we go up to R. We could, if we wanted, go from P up to Q, then Q to R, but we don't know this journey here, P to Q. So we have to use the stuff we know. We have to use the journeys we know and we're aware of. So we have to go from P to S, then S to R. Well, P to S, given by the vector S, then S to R is given by the vector Q. So it's S plus Q. That there is this journey here in the middle. The last one we want is the vector Q to P. So that's this one here. So that's Q to P coming back down this way here. Now to get from Q to P, we have to find a journey that we know. Well, first part is Q to R. We know that part, we can go there. The next thing we then want to do is go from R to P. So we want to go down this journey here. I'll break it down into stages. Q to R is going back the way in this R vector. So it's negative R. We then want to go R to P. Well, we know that P to R is given by this. So R to P is going back the way in that journey. So it's then take away the S plus Q. We're going back the way in it. We then just simplify this and we get our answer. So it's negative R minus S minus Q. That's the vector journey there. We could write these in any order, but that's essentially what we have to get an answer of this form. When you're working in vectors, it's important that you use logic. So looking at the journeys we know, using these to represent other journeys and other pathways in our system that we have. Bear these all in mind when you're working through them, and you'll be fine.